In this video, we're going to be talking about exponential models. So I'm going to show you exponential equations, generic ones, and then we're going to model it after real-life examples. So first off, an exponential model is going to look something like this. 2 to the x, 3 to the x, 4 to the x minus 1. So we got this being our base, this 2 here. Okay, so if I just take my normal calculator, and if I was doing this all by hand, I'm going to pick all these x values, and then I'm going to plug them in for x to figure out what I want for y. So the first one, I would do y to the negative 4. So when I type that in, I want the decimal, so I'm able to graph it, and that is 0.0625. I'm going to change colors here. 0.0625. Okay, my next one, if I type in 2 to the power of negative 3, I get 0.125. 2 to the power of negative 2, I get 0.25. 2 to the power of negative 1, I get 0.5. Anything to the 0 power is 1. 2 to the first is itself. 2 squared is 4. 2 to the third is 8. Okay, so if I graph that, remember you go left or right and then up or down. So I go left 4, 1, 2, 3, 4, pretty close to 0. My next one, I go left 3. Oops, I'm on the other side. There. Left 3, a little higher than that. My next one, I go left 2, a little higher than that. My next one, I got, we need to scoot them all down. So it should be here. We're getting a little bit higher. This one's 0.5. I got at 0, 1. There we go. 1 to the right 2, or right 1 up 2, right 3 up 4, or right 2 up 4. 1, 2, 3, 4. And my last one, I go right 3 up 8. Okay, so if I were to graph it, it looks something like this. Okay, if you look on your graphing calculator, I will get closer and closer to 0 values for my y. I will never cross my 0 value until I will never get a negative 1 for my y values. I'm just getting closer and closer to 0. Okay, so when I'm talking about asymptotes are basically the line where my actual line will never cross. So it's kind of like a wall. It's this wall of where my actual graph will never cross. So it never crosses this line here over to the other side. It gets closer and closer to it, but it never crosses it. Okay, that line represents y equals 0. It's my x-axis. So it will never cross that line. Think of it as a wall. You never cross over a wall. Okay, you just run into it. So you can run into it as long as you don't cross it. Okay. So my next one, if I wanted to, I could just type this in my graphing calculator. So I type in y equals 1 divided by 3, and then I do the caret button and x. So when I press graph, I get a picture. Okay, and then once I want my table values, I'm going to press second and graph again. Negative 2, I have 9. Negative 1, I have 3. 1.33 repeating, and 0.11. Okay, so I go left 2 up 9. I go left 1 up 3. I go 0, 1. And then it looks like we're getting closer and closer to 0 again. Okay, so if I look at my table, I can move up and down in my table. I'm going to get closer and closer to 0, but I'm never going to hit 0. So we got y equals 0 as my horizontal asymptote again. So it's this line that it's not crossing. Okay, so when we're talking about the parent function always looks like this. Okay, b sometimes could be 2, it could be 3. That's kind of what we were working with in our last ones. Okay, so my shifting occurs when there's something in front of that b, when there's something with my exponent, or when there's something outside here. Okay, so a will be my shrinking and compressing. Okay, so if it's bigger than 1, it will stretch it. Oops, I said shrink and compress. I meant stretch. Stretch and compress. Okay, so if it's bigger than 1, it will stretch it. If it's between 0 and 1, it will compress it. If it's negative, it's a reflection over the x. Think of that negative being outside. You want to keep your x outside. You're reflecting over the x. Okay, when I look at h, think of that as being inside. So when we were in the inside of the absolute value, we are moving left and right. And remember, it's always opposite of what direction you normally think it would be. Normal direction. and then k is my up or down. Reflection over y would be if this x is negative. Okay, so my first example, we have a negative in front, so it's going to be a reflection over the x. Okay, it is not a stretch of 2 because that's my base. It's only when there's a number in front of that 2 that it's going to be a stretch or compress. Okay, so I'm going to go ahead and type this in my graphing calculator. So when I do, I press y equals. I use the negative button, not the minus sign. 2 to the caret of x. I press graph so I can see what my graph looks like. It should be reflected over your x-axis. I press second and graph again to get my table. Okay, and then I want to pick values that aren't super close together. So if I look and scroll up, -5 and -6 and -4, they're all like 0.01, 0.03, 0.06. That's going to be extremely hard to graph because they're so close together. So I'm going to start mine at -3. So I'm going to do -3, -2, -1, 0, 1, 2. Okay, so -3 I got -0.125. -2 I got -0.25. -1 I got -0.5. And 0 I got -1, -2, -4. Okay, so if I graph this, I'm going to pause the video. Remember, you go left or right and then up or down. So your graph should look something like this. If you scroll up on your table, you can see that it's getting closer and closer to 0, but it's never crossing that 0. Okay, so the asymptote again is y equals 0. It's getting closer and closer to it. My next one, okay, my +1 means I am going up 1. That -2 is going left or right. It's always the opposite of what you think. So we're actually going right 2 when I graph it. Okay, so I'm going to type in y equals 4. When I do my caret, I make sure x minus 2 is all the way in it. So you might need to type in x minus 2 in parentheses. Okay, because that -2 is up there in its exponent, you need to make sure it's together in the exponent. So write it in parentheses, and then you're going to have to get out of it by pressing the over button, and then +1. Okay, so I graph it. It looks like it is shifted up 1 and shifted to the right 2. I press second and table to get some table values. It looks like we're getting closer and closer to 1, because if you go more to your negative x's, we're getting closer and closer to 1, but we're not crossing. So my asymptote's going to be at y equals 1. Okay, so let's pick some values. It looks like a lot of these are pretty close, so let's start it at 1, 2, 3, 4. Okay, if you notice, 4 is going to be off my graph because the y value is 17 and my graph does not hit at 17. Okay, so I'm really going to be graphing 1, which is 1.25, 2, which is 2, and this is 5. So I'm going to graph those super quick. Okay, so your graph should look something like this. Your horizontal asymptote this time is at y equals 1, so it's getting closer and closer to 1 but not crossing it, and then it should look something like that. Okay, this one, we have it going down 4. We have it going left 1 because that +1. We have it stretching by 3 because then that negative means it's a reflection over the x. Okay, so I'm going to go ahead and get my t-chart here. Okay, so make sure when you type it in, you type in y equals 3. You add your parentheses. So parenthesis 2 to the, and then these also need to be in parentheses so that they're together. So parenthesis x plus 1, end your parenthesis. And then you need to make sure you still add this one. Okay, so you need to end the parenthesis that's with the 2. And then -4. And then you're going to press graph. You're going to press second graph to get the table. Okay, it looks like it's getting closer and closer to -4 this time. It's not crossing that -4 on my y, so that's where my horizontal asymptote's going to be. So I'm going to pick some values. Let's do -3, -2, -1, 0, 1. So -3 sits at -3.25, -2.5, -1, 2, and 8. So I'm going to graph these. So your graph should look something like that. Your asymptote right here is at that y equals -4, so it gets closer and closer to it but does not cross it over. Okay, my next one, we're talking about exponential growth and exponential decay. So for it to be exponential growth, it's going to be growing, so that's my growth. Exponential decay, it will be decaying or decreasing. So that's my exponential decay. Okay, so we're using the exact same equations for it. This y equals a to the bx. Okay, we normally we're having the b to the x in it. Whenever b is greater than 1, it's going to grow. Just like how when we are stretching something, it needs to be greater than 1 for it to stretch. Okay, and then it's going to decay if it's between 0 and 1. Because if I multiply something times a half, it's going to get smaller. It's going to decay. All right, so then a shortcut to be able to figure out what you're crossing on your y-axis, so these points right here, is just looking at the a value or the number that sits in front of that equation. So I'm going to show you some examples of this. So first off, if this number is less than 1, it's going to be decaying. Okay, and then my y-intercept, I said we look at our a, so it's going to be 0, 12. The reason that works is because I got y equals 12 to the 0.95. If I'm trying to find where it's crossing my y-axis, I plug 0 in for x because that point is always 0, comma, whatever the number is. Okay, so anything to the 0 power is 1. 12 times 1 gets me 12, which is what my answer is. So whatever that front number is, it's going to be where it's crossing your y-axis. My next one is bigger than 1, so it's going to be growth. And my y-intercept this time is 0.25. So if I graph that on the calculator, you would see it growing, and then it would cross your y-axis at that point right there. Okay, so here's an equation. So when we want to throw some real-life examples in it, this is what we're going to use. So this is going to be the amount that we have after the time period that we put in. This is going to be the rate that it's either getting bigger or smaller, the initial amount of the population or money, and T stands for time. Okay? So the reason that we have this in here, it looks, if we wrote it out, very similar to this. Okay? It's got that exponent here for time. This B represents this. So B, I said, if it was bigger than 1, it's going to grow. Okay? So it's going to be the same concept. When I add that rate to it, if it's bigger than 1, it's going to be a growth. If it's less than 1, so if I have to subtract my rate and it's less than 1, it's going to decay. Okay, and then A stood for the initial amount, so the spot where it's crossing over into the positives. So my first example, you invested $1,000 into a savings account at the end of 6th grade. The account pays 5% annual interest. How much money will be in the account after 6 years? So let's circle the things I actually care about. Okay, we got $1,000. 5% annual interest for 6 years. Okay, interest means if I put my money into an account, the bank is going to pay me to keep it there. It's going to be a very small percentage, like this, but it's going to pay me some cents for me to keep it in their account after an amount of time. Okay, so when we use our equation, I have this time, or this initial amount, and then I have 1 plus the rate that I have. I can't put 5% in my calculator. I need to put the decimal, so 0.05 to the amount of time of 6 years. Okay, so this is going to say after 6 years, how much is going to be in my accounts for keeping that $1,000 in there, plus adding on to it what the bank's paying me to keep it there. So I'm going to type in 1,000, 1 plus 0.05 to the 6. So I will have $1,040.10. So I kind of gained around $340 by keeping it in that bank. Okay. Also, if I add 0.05 to 1, it's going to be 1.05, which is bigger than 1, which means it should be growing. It should be a growth, which it did grow. Okay, my next one, I got $500 in this account for 3.5% in 5 years. So I got my initial amount being $500. My rate this time is 0.035. And my time is for 5 years. So 500 times 1 plus 0.035. And my parentheses, caret button, 5. So after 5 years, I will have $593.84. Okay, we can also talk about population. So we might not do exponential growth and decay with just money. We could also talk about populations growing and declining. Okay, so we're going to use the exact same formula. So I got I'm going to zoom in here. AT equals my initial amount, so the 120,000 people. Okay, my rate of that it is growing. So if it's growing, that means this needs to be bigger than 1. So if I do 1 plus my percentage of 0.012, and then my time period, 15. So if it's growing, that means my number should be bigger than 120,000 after this time period. So I'm going to take 120,000 times 1 plus 0.012 to the 15. Okay, my population after 15 years is 143,512, and I can't have 0.24 of a person, so we're just going to leave it like that. Okay, my next one, it's declining. So if it's decreasing, I need an exponential decay, which means this right here needs to be smaller than 1. So I have my initial amount being 1860123 times 1. I need to subtract it this time by my percentage, okay? Because if I do 1 minus 0.015 in my calculator, I'll have 0.985, which is smaller than 1. If it's smaller than 1, it should decay over 12 years. So when I type this in, my number should be smaller than this one because it's decaying. 1 minus 0.015. And I get 155,148. Ooh, hello. 155,148.5. Okay, and you can see that that got smaller. Okay, so just be wary if you need a minus sign or plus sign in there. Okay, we also have this thing called continuously compounding interest. Okay, it's got the initial time, it's got our principal time, so our amount that we started with. This E stands for the exponential. We've been talking about exponential growth and decay. That's what the E is. T stands for time, and R is going to stand for the rate again. Okay, so in all of these problems, you need to see compounded continuously to do that. What compounded continuously means is basically you're getting interest on your interest. Okay, so normally you are gaining interest in a time period like between 6 and 12 months or every other year. Your bank is giving it to you. Okay. This is you're getting interest on top of that. Okay, so I have a link to this video that will explain this way more in detail. Okay, so it's like if you put $10,000 into a bank with a percentage of increase or percent of interest, okay, at the end of the year, let's say you gained $500. Now you have $10,500. You put it back into your account and gain interest off that total. Whereas when we were compounding it or when we were doing it before, the simple interest, you wouldn't make it off of that. You would make it off of only your 10,000 original. So please watch this video. Compounding continuously will make so much more sense if you Google that. Okay, so suppose you won a contest in 5th grade that deposited $3,000, 5% for 4 years. Okay, so this time we're using the model PERT or PERT. Okay, so P stands for my initial amount. My exponential, my rate this time is 0.05. times my time of 4. Okay, so we should be gaining a lot more money than when we do a normal simple interest problem. So I got $3,000. I have to press second and then the button that says ln, which stands for natural log. It will give me my exponential in any calculator. 0.05 times 4. So this one I have $3,664.21. You gain a lot more money when you do it compounded continuously. Okay, suppose you invest $1,600, 5.6% for 4 years. So I got A of T is equal to 1,600, E to my rate of 0.056 times 4. So 1,600. Second, the one that says ln to get my exponential, 0.056 times 4. I got $2,171 after 4 years.